Welcome everyone, glad to have you along. What we're going to work with in section 13.7 is modeling with sine and cosine functions. And whenever you're modeling with any kind of function, what it means you're doing is you're writing equations that would represent some situation, and we're going to represent certain situations, certain kinds of problems with sine and cosine equations. This is the way this is going to work out. Now the learning goal is that you're going to solve word problems using periodic, sine, or cosine functions. So, got a couple problems for us to work with here. Let's go ahead and jump into this thing. Alright, first problem. It says, as the tide rises or falls, the depth of water below a boat sitting in the harbor continuously changes. During low tide, the boat is 2 meters above the ocean floor. 6 hours later, during high tide, the boat is 12 meters above the ocean floor. Assume high tide occurs at 2 a.m. Alright, so as you know, the tide changes all the time, and there's a high tide every day, there's a low tide every day. In fact, well, alright, I'll get to that here in a little bit, but high tide, low tide, you understand that situation. So this boat here that's sitting in the water, it keeps rising and lowering in comparison to the ocean floor just because the tide is changing. What we're supposed to do first with this information is we're supposed to write a sine function that describes the boat's distance d above the ocean floor as a function of time, t. Now let's add a little detail there. We're going to measure time in hours, and specifically what I'm going to do is I'm going to say that 1 a.m. for instance is the first hour, 2 a.m. is the second hour, 3 a.m. is the third hour. That would mean midnight is 0 hours. Alright, follow me? Okay, so how are we going to take this information about when the high tide is and when the low tide is, and how high the low tide and the high tide are? How will I take that information and make a sine function that would tell you at a certain time of day, essentially, how high the tide would be? Alright, well the first thing to understand here is that a tide is a periodic thing. It keeps coming and going. It keeps fluctuating between low tide and high tide, low tide, high tide, low tide, high tide. And anytime you have repeating values, you know you can use a sine or a cosine function to model that. So we're just going to use the sine function, right? And then secondly, what we're going to do is we're going to make use of a few key pieces of information. Now those key pieces of information that we're going to use are going to be, first of all, the 2 meters above the ocean floor at low tide, okay? Because what that tells us is the minimum height or the minimum depth of the water below this boat. And we're going to use the fact that 6 hours later, it's high tide, and at the high tide is 12 meters above the ocean floor. All right, all that is super important information. Now let's think about what we can learn from each of those pieces of information. Basically, we know that our equation that we're going to write is going to have to be in the form y equals a times the sine of b times x minus c plus d. All right, that's what we've been working with in this chapter, correct? And so we can use the information that was given to us to help find those values. For instance, we know that the minimum value here for y is equal to 2, and we know the maximum value is equal to 12. That's going to be very important for us, because what we can do with that is we can find out what would be the amplitude of this function. We can say then that the absolute value of a would equal 12 minus 2 over 2, and that's going to equal 5. So now we know part of this equation, don't we? Secondly, we can find out what the value of d is with that. What was the vertical shift for this function? Because d would just equal 12 plus 2, the max plus the min, divided by 2, and that would equal 7. All right, now there's a little bit more that we can learn with the information that's given. I want to try to start graphing this information over here because I think it's going to make it a little bit easier for us to understand. Now on the graph, the horizontal axis is going to represent the time in hours. And then let's say that the horizontal axis, sorry, the vertical axis is depth in meters. And let's go ahead and label a few measurements here. I'm going to make every interval on the horizontal axis go by 2, so this would be 2, 4, 6, 8, 10 right there. 20, and so forth. Now, why were those intervals appropriate? Because there's 24 hours in a day, and our time represents what time of day it is, essentially, in hours, and so it makes sense that we don't need to show anything really above 24 right there. We can, but we don't have to. And then as far as the depth, it makes sense to just go by ones here on this vertical axis with the intervals that I've got, because I can make that 5, 10, and 15. And the depth never gets above 12 meters anyway, so we're kind of covered there, aren't we? All right, now let's go ahead and make the graph. Let's graph a couple points that we know. We know that at 2 a.m. is when high tide occurs, correct? So at 2 a.m., we know that the tide is going to be 12 meters, and so we can plot the point 2, 12 right here. Then we know that 6 hours later, that would mean 8 a.m., correct? Oh, I tell you what, 6 hours later, the high tide is 12 meters. So the high tide occurs 6 hours after the low tide, doesn't it? Now, 6 hours before 2 a.m. would be 8 p.m. or 2000, as it turns out. So when the time is equal to 20, we know that we're going to have a low tide, and we know that low tide is going to be 2 meters. So we'll go ahead and graph that right there. All right, and let's go ahead and see what's in between. Now, we've already figured out a couple values here. We already figured out our amplitude was 5, and we already figured out that the value of D, our vertical shift here, is 7. So that means we can graph our midline value. I'm going to go ahead and do that. At 7, let's graph this. So I'm going to go back and make it dotted real quick. And now I can talk about what else we can learn about our equation with this whole 6 hours information. Okay? The 6 hours, the amount of time between high tide and low tide, is really helping us try to figure out what is the period of a high tide, low tide cycle. How long does it take before it repeats? Well, I think you can infer from that it would take 12 hours, correct? Because it takes 6 hours to get from one to the other. So it would take 12 hours to get, say, from low tide to low tide, or from high tide to high tide. All right, and our graph will kind of bear that out then. Every 6 hours we shift, right? So if I'm talking about at 8 p.m. right there at 2000, that would mean at 1400 we would have had a high tide, right? And then 6 hours before 2 p.m. or 1400, at 8 a.m., we would have had a low tide, so right here. And so we kind of get a graph. Now I'm going to divide that up a little bit more. Halfway between the high tide and low tide, you would assume you're at middle tide. So at t equals 5, right here, we would have a middle value. And every 6 hours we would have a middle value as well. Let me fill those in. And here would be a graph of that sine function that we're going to create. Now in terms of making our equation, I've already talked about the other two values that we need. Well, I've already talked about one of the other values that we need to find out, and that's the value of b. Because we know we can find the value of b by doing 2 pi divided by the period. And what we discussed is, since the tide starts over every 12 hours, is that the period is going to be equal to 12. So the absolute value of b is going to be 2 pi over 12, and that's going to be pi over 6. All right, and then let's think about our value of d. And in order to figure out what the value of d is, we need to think about where does this sine function begin compared to where it normally would. Now, normally it would start on the x-axis, on the y-axis, correct? But instead, we get a middle value here when t is equal to 4. And we go downwards, don't we? Now, that actually indicates to me that a, the fact that we go downwards, is going to indicate to me that a is negative 5. So I'm going to go ahead and write that. A would be negative 5. and the fact that the starting value is 4 hours greater than what it normally would be, all right, it's 4 units to the right, tells me that my C is going to be 4. Now I've written a lot of things in there. I'm going to erase it so I've got room to actually write the answer. What is the function that describes the motion here? And that would simply be this. All right, the depth d instead of y, because we are saying this is depth. The depth would equal -5 times the sine of pi over 6 times t minus 4 plus 7. All right, now if you need help with writing those equations, go back and watch the previous video that I made on writing equations, but you kind of saw how I found out what the values of a, b, c, and d were there, right? Okay, now let's actually use this for something. We're going to answer some questions other than just what's the equation for the depth of the water. Starting with, how deep will the water be at 4 a.m.? Okay, well now that we have a function that will model the depth of the water, what we can do is we can simply plug in a given time into that function, and it will help us go ahead and determine how deep the water will be at that time. So what we're going to be doing here is taking our equation, and we're going to be finding out what is d of 4. And then that would of course be equal to -5 times the sine of pi over 6 times 4, because that's our t, minus 4 plus 7. Now you can use your calculator to evaluate that, but actually you shouldn't need to, because the 4 minus 4 is going to be 0. 0 times pi over 6 is 0, and the sine of 0 is 0, and -5 times 0 is 0. 0 plus 7 is 7. So we know at 4 a.m. the water level is going to be 7 meters. Okay? Well, now we can kind of do a similar thing and figure out at what time will the water be 8 meters deep. Now in this case, what we're going to do is we're going to set our function equal to 8. We want to know for what time is d of t equal to 8. So I want you to use your graphing calculator at this point. This is one of those that we would solve on the calculator. And I want you to make one equation that is just simply your function that we wrote to model the water depth. This expression right here, you put that in your y1, and then in your y2, just put the value of y equals 8. And make your window settings go from 0 to 24. Make sure your calculator's in radians. Right? We're not using any units here, so we're assuming everything is measured in radians. And go ahead and solve for the t on that interval. But let me show you kind of in the picture exactly what you're going to be looking for when you do that. We're simply going to be looking for all the places where the line y equals 8 intersects the graph of our function. So if I were to draw this line y equals 8, it looks like there are 1, 2, 3, 4 times. Let me make those a little bigger. There are 4 times throughout the day where the height of the water would be 8 meters. All right, so you're just finding 4 intersections of the line y equals 8 with this trigonometric function right there. Now I'm trusting that you know how to do that. If not, I've got calculator instructions for solving equations in another video as well. That's beyond the scope of this video in particular. But I am going to go ahead and write down what those solutions are. All right, the first such value occurs at 3.6 hours, so, you know, after 3:30 a.m. sometime. The next occurs at 10.4, so just a little before 10:30 a.m. And then we technically don't really even need to use our calculator to find the other values, because remember, the tide returns to its current level every 12 hours. So we know that this value right here would just be 12 hours after 3.6, because that's when it hits 8 meters on the way down. All right, so that would be 15.6 hours, so a little after 3:30 p.m. And then this last value is when we hit the 8-meter mark on the way back up. And so that's going to be 12 hours after it was the first time. 10.4 plus 12, 22.4. So t equals each of those values will be the answers to part 2. Very good. All right. Now, last question here says that the boat cannot sail. This is the last question for this problem. Says that the boat cannot sail when the water is less than 9 meters deep. And it wants to know during how many hours a day can the boat sail. All right, I'm going to erase some things from the graph here so we can use our graph a little more effectively to answer this question. This turns out to be a very similar question to the one that was just asked, in that essentially what we want to do first is we want to figure out when is the depth of the water below the boat going to be 9 meters. All right, and so we'll go ahead and draw a line at y equals 9, and we're trying to figure out how many times during one 24-hour period will the water level be exactly at 9 meters. Okay, and then after that, here's what we're going to do. We're only concerned with when the boat can sail, right? And the boat can only sail when the water is, well, greater than 9 meters. The boat cannot sail when the water is less than 9 meters deep, so it can only sail when the water is at least 9 meters deep. So we're going to have to figure out how many hours does this little bit include, and how many hours does this little bit include. And if this is during our 24-hour time frame right here, then we'll figure out, how many hours are included there as well. All right, let's check it out. So let's write and solve this equation. All right, we're just setting this same thing equal to 9 instead of 8 as we were a moment ago. And then we'll solve the same way we did. We want to find out where are these points of intersection. And I'm not certain if this one will be before midnight or not, but let's go ahead and see if it is. All right, so really, just like we did last time, we can just find these first two values. Okay, when the tide is going down, when does it hit 9 meters? And when the tide is going up, when does it hit 9 meters? And then we can find the corresponding things for when the tide is going down and when the tide is going up just by adding 12 to each of these values, adding one full period to each of those values. Now that first point of intersection is 3.2, so that's a little before, that's probably 3:15 a.m., a little before 3:15 a.m. There you get 10.8, so a little after 10:45 a.m. And then let's add 12 hours to each of those. This would be 15.2. And this would be 22.8. Yep, all those fit within our 0 to 2400 time frame, don't they? So there are 4 points of intersection there with the line y equals 9. Now again, what we care about is this part right here. How many of those hours are above 9 meters? Okay? Now really kind of the smart way to do this is this way, I think, because it's a little bit tough to tell how many hours there are between 22.8 in the PM and 3.2 in the AM. All right, not incredibly tough. I'm sure you can think of ways of making that happen, but essentially it's going to be the same as this difference right here. Now, if I want to know how many hours there are from this point to this point, all I need to do is subtract those times, right? And 15.2 minus 10.8 is 3.4. And we can really just say then that 3.4 times 2 would be the total number of hours per day that this boat could sail. So 6.8 hours during the day, this boat would be able to sail. All right, pretty cool process. That's how you go about solving a word problem using trigonometric functions. Now I'm going to show you one more, a little bit shorter version, and then we'll be done with this. Let's go ahead and take a look at this problem right here. And what this one tells you is that the average number of sunlight hours, S, during a month T, where T equals 0 corresponds to January, is modeled by the function S of T equals, and you see what S of T is equal to right here, a bunch of variables there. And the first thing we're going to try to do with that information is we're going to try to find the values of P, Q, and R, which would represent the vertical shift, not the vertical shift, but the vertical stretch, and the horizontal shift, and the vertical shift of this particular function. Okay, now similar to what we had last time, you know what, I'm realizing the entire problem is not set here. Let's take a look at some more here. There we go. It says the city averages 14 hours of sunlight per day in June and 10 hours of sunlight per day in December, and these are the maximum and minimum sunlight hours for the year. Now, based on that, we're going to try to figure out what this equation is that will tell you how many hours of sunlight per day is averaged in this city depending on the month, T, that you're in. Okay, now I'm going to kind of make a little graph to help us out here just like I did with the last one. Let me label my axes down here. We're talking about time in months. And as we're looking at the months January through December, it makes sense just to go by ones here on my horizontal axis. So this would be the 5th month, May. There's the 10th month, October. Here's the 15th month, which, well, I tell you what, I said the 5th month was May. But what we're saying is that t equals 0 would be January. So that would be January right there. And then February would be 1, March would be 2, April 3, May 4, and so forth. So everything's shifted over a little bit from what you're used to seeing. All right. And then the vertical axis is going to be the number of sunlight hours. Per day. And it should be safe to go by ones there as well because we don't have any numbers bigger than 14 to display. So let me do that. All right. Now, in June, we're going to have 14 hours of sunlight. So January is 0, correct? And so here's February, March, April, May, June. Turns out to be 5 months after January. That's how that 5 is going to work out. And then 5 months after January, we know that there's going to be 14 hours of daylight. So let's plot the point 5, 14. And then in December, you only get 10 hours per day. Now December would be 11 months after January, correct? So we'll plot the point 11, 10 right there. And those are our maximum and minimum values, correct? So based on the maximum and minimum values, we could figure out what the middle value is just by adding them. 14 plus 10 is 24, divided by 2 is 12. Now I'll go ahead and plot y equals 12 there. And let's see if this makes sense to you. If we average 14 hours of daylight in June, 5 months after January, wouldn't we also average 14 hours of daylight the next June, which will be 12 months later, or 17 months after January? So I'm going to plot a point right there. And kind of similarly, 11 months after January, we average, 10 hours per day. So if we go another 12 hours all the way up to 23, it would be somewhere around here, we would be averaging that same amount again, right? Now what I'm trying to show you here is basically what is the length of one period. And the length of one period from peak to peak or from trough to trough happens to be 12 months, right? So that's our period. And that's going to help us find some values here. Now let me go ahead and make the rest of the graph. Now every 12 months we start over, don't we? Every 6 months you go from the high to the low value. That means every 3 months you would kind of get to your mid value, correct? So 8 months after January, you'd be at 12 months. And then, let's see, this was 11. So then 14 months after January, you'd be at your low value, as your middle value, 3 months before here, so 2 months after January, you'd be at your mid value, and so forth. So this is what the graph would look like over the interval that we're trying to work with here. Now from this, you ought to be able to see these things pretty clearly. First of all, you know that the absolute value of P is going to have to equal the max minus the min divided by 2. So 14 minus 10 divided by 2, and that's 2. Now that's what the absolute value of P is. And then we need to think about whether P should be positive or negative. Well, we are working with a cosine function, correct? So if we're looking at our x-axis and we're trying to see where does the nearest maximum or minimum value occur, we're going to have to look at a maximum value because we don't know where this minimum value occurred over here. And that maximum value happens to be at t equals 5, correct? Okay, now since we're starting at a maximum value, that means that our a is going to be positive 2 as opposed to negative 2, correct? All right, now let's go ahead and worry about the q, which is kind of the next thing I was getting at. Our maximum value is starting 5 units to the right of the y-axis, isn't it? So that would imply to us that q is equal to 5. And then R is the vertical shift. Well, R being the vertical shift, that's going to correspond with our midline right there, or the max divided, or plus the min divided by 2. So we've already figured out that that is 12, didn't we? So there's our values of P, Q, and R. Now, by the way, you didn't have to find out what the value of B was here, but the way you would have found it is that you know the period is equal to 12, because 12 months in a year, that's really what that boils down to here. And so the B was equal to 2 pi over 12, which was pi over 6. All right, now let's use that information to answer one more question, then we'll be done. Let's figure out during which months of the year there are no more than 9.5 hours of sunlight per day. All right, we're going to change that to 10.5 actually. And simply all we're going to do is we're going to find all the places where this graph intersects the line of y equals 10.5. We'll go ahead and graph that. And then we'll just figure out which months does that correspond with. Now it looks like we're going to have 3 locations here that we're going to try to find. The fourth one kind of looks like it's out of the way. And truly there's only 2 locations we've got to find, right? Because if we're just looking on a January to December basis, and this is January right here, and t equals 11 is December, I can just kind of stop there. I'm going to draw a vertical line to kind of show where my boundary is. Yeah, so truly just here and here, this is what we care about. All right, so graph the function y equals 2 cosine of pi over 6 times x minus 5 plus 7 in your y1. Go ahead and graph the function y equals 10.5 in your y2 and find out these 2 places where they intersect. What I would do is, all right, a calculator should be in radians, and let's make 0 less than or equal to x less than or equal to 12. That's really the only interval we care about here, right? And let's go ahead and find those 2 points of intersection. Sorry, that 7 was from the last equation that we had. We had plus 12 here, right? Now the first value is 0.38, which means when we're 0.38 months past January, we're getting at least 10.5 hours of sunlight. And so that means we haven't quite made it to 1 month past. That means we're not in February yet. So in January, you're getting fewer than 10.5 hours for sunlight. That's what that tells me. Then let's see what this value is right here. And that'll get you about 9.6. And so 9.6, we're talking almost 10 months after January, but not quite. 9 months after January would be October, right? And then, of course, we're not going to get above 10.5 hours of sunlight again until we get back to to January, and then February. So we can say in October through January, or that's during which months? October, November, December, and January, our function tells us that we would be getting no more than 10.5 hours of sunlight per day. Pretty cool the way periodic functions can be used to solve questions involving values that repeat themselves on daily cycles, on monthly cycles, on annual cycles, and so forth. Thanks for your attention. I know this is tough work right here, but you're capable of handling it. I'll see you later. Good luck.